continue our discussions on kinetics of a system of particles. In this lecture, we will carry forward our discussions on the kinetics of a system of particles, and we are going to look at the impulse momentum relation and finally define the angular momentum. Now, the impulse momentum form of the generalized Newton's second law for a system of particles. Let us look at the position vector of the ith particle. We are representing the position vector of the ith particle in terms of the position vector of the center of mass and this relative vector with respect to the center of mass, the relative vector of the ith particle with respect to the center of mass rho I, which I can differentiate and get this velocity relations. So, the velocity of the ith particle is velocity of the center of mass plus the relative velocity of the ith particle with respect to the center of mass. Now, we define linear momentum of the ith particle as mass of the ith particle times the velocity of the ith particle, and by using the expression above we get, and summing over all the particles, we get the linear momentum of this system of particles as capital G vector is summation of m I r g dot, this is the velocity of the center of mass, plus m I rho I dot is the velocity of the ith particle relative to the center of mass. And when I do this summing over, I get summation of m I, which is the total mass of the system times velocity of the center of mass, and the second term under summation, which is summation of m I rho I dot, goes to 0 because of this identity that summation of m I rho I is 0. Now, Newton's second law, the generalized Newton's second law for the system of particles. Let us start by differentiating this linear momentum of the whole system. Therefore, if I take time derivative of capital G vector, I get mass times acceleration of the center of mass, and mass times acceleration of center of mass from Newton's second law for the system of particles is equal to F, the force, net force acting on the system of particles. Thus, rate of change of linear momentum of the whole system is equal to the net force acting on the system. So, this generalizes Newton's second law for a particle, but only thing you have to remember that we we are discussing about the acceleration. This involves the acceleration of the center of mass. If I integrate over time, I get the change of linear momentum of the system equal to the impulse of the force between two time instants. So, this is the linear impulse. So, what we have seen here is that the linear momentum of the system is related to the velocity of the center of mass, the total mass of the system times the velocity of the center of mass, and rate of change of linear momentum of the system is equal to the force, net force acting on the system, and integrating this generalized Newton's second law, we obtain the linear impulse momentum relation. This is our impulse momentum relation. If there is no external force, then linear momentum of the center of mass is conserved. Here what we notice once again that internal forces do not contribute, because it does not contribute in the Newton's second law, generalized Newton's second law for a system of particles. Let us look at an example problem. This is taken from the book of Merriam and Craig. Two small spheres treated as particles, each of mass m, are connected by a cord of length 2b. measured up to the sphere centers. They are initially lying at rest on a smooth horizontal surface. So, these two mass points connected by this inextensible string of length 2b, it is lying on a smooth horizontal surface. A body of mass m naught traveling in a straight line with velocity v naught hits the chord perpendicularly in the middle, causing deflection of the two parts as shown. So, what is shown is, once this body of mass m naught, which is coming at a velocity v naught, hits the chord starts wrapping on that moving mass. Determine the velocity v of the mass m naught as the two spheres near the contact, they come close to contact. That means, these two spheres, as shown in the third figure, on the rightmost figure, the two spheres will be moving close together and they will be coming in contact. So, when theta approaches 90 degree, where theta is defined in the second figure, when theta approaches 90 degree, these two spheres will come and collide. So, we have to find out the velocity v of the mass m naught as the two spheres near contact with theta approaching 90 degree. Also find d theta dt for this condition. Let us consider these two states of the system. I have marked in red 1 and 2. State 1 is just before the moving body hits the chord, and state 2 is when these two spheres are nearing contact. So, which means theta is approaching 90 degree, it is almost 90 degree. Theta is almost 90 degree, that represents state 2. I have considered general velocities. When theta is 90 degree, I have considered the vertical velocities of these two spheres as u1 and u2. It has been marked, but they are also moving along with that body of mass m naught. So, these are the relative velocities of the two spheres. The net external force on the system, there is no external force on the system. So, that is 0, net external force is 0, therefore, linear momentum of the center of mass of the system must be conserved, and there is no dissipative force. Therefore, the energy of the system must be conserved. There is no dissipative force, no work done by any other force. Therefore, the total mechanical energy of the system must be conserved. Now, from the first condition of conservation of linear momentum, I must have that the net linear momentum in state 2 must be equal to the net linear momentum in state 1. In state 2, what is the net linear momentum? It is m naught, which is now traveling with velocity v I cap. Now, I am using the coordinate system shown here x y. The whole motion of m naught was taking place in the x direction. Therefore, its linear momentum in the final state when theta approaches 90 degree is m naught v I cap plus mass of the lower sphere. This one is m, mass of the lower sphere is m times velocity, absolute velocity of the lower sphere, and that is moving with velocity v in the x direction, I cap direction, and u1 in the j cap direction, plus the upper sphere, mass of the upper sphere m times velocity in the horizontal direction, which is v I cap, and minus u2 j cap. So, u2 is the relative velocity. Therefore, the total the absolute velocity of the upper sphere is v I cap minus u 2 j cap, and hence the momentum, linear momentum, is mass times this velocity, and this is the net linear momentum, the total linear momentum of the system in state 2, and that must be equal to the total linear momentum of the system in state 1, which is nothing but m naught v naught I cap. The spheres were not moving in state 1. When I simplify and look at the I component and j component of this vector equation, I observe from the I component this relation, and from the j component I have u 1 must be equal to u 2, and I call it a common velocity u, and this is a relative velocity, remember, and this must be equal to b times theta dot. B is half the length of the chord. This is in state 2. Therefore, here theta is equal to 90 degree, this must be remembered. In state 2, theta equal to 90 degree. Therefore, from here I obtain the final velocity of mass m naught as this expression, which is straightforward algebra. Now, we look at energy conservation. Energy in state 2 must be equal to energy in state 1, because now I have to find out the velocities of the individual spheres, and that must imply that the total mechanical energy, here it is only kinetic energy, there is no change in potential energy, because everything is moving on a horizontal surface. Therefore, the total mechanical energy or the total kinetic energy in state 2 is half m naught v square, because m naught is moving with velocity v, plus 2 times the velocity of these the kinetic energy of these individual spheres or individual particles, and that turns out to be half m v square plus u square. Always remember, this is calculated in state 2, which is when theta is equal to 90 degree. Therefore, the total kinetic energy of the two spheres is m times v square plus u square, and this final kinetic energy must be equal to the initial kinetic energy, is half m naught v naught square, and from here, by substituting that expression of v that I just now obtained, I have substituted it here. This one is v, this is v square actually. So, if you substitute that expression and finally solve straightforward algebra, you will obtain theta dot as this expression, and we have also obtained the velocity in the previous step as this. Therefore, we have obtained the final velocity of the combined system and this rate of change of theta when theta approaches 90 degree. That means, these two spheres are coming in contact. Now, we will define angular momentum and look at angular impulse momentum relation. Once again, we have this system of n particles as shown on the right. We will write Newton's second law for individual particles. For the first particle I have written, and like this I can write for the nth particle. So, all the n particles I can write Newton's second law. Now, I take cross product of individual equations of the particles with r I vector, but here it is very important to note that it is r I cross the Newton's second law for the ith particle. So, for the first equation I have r 1 cross Newton's second law for the first particle. For the second particle, it would be r2 cross the Newton's second law for the second particle, and so on. For the nth particle is rn, the position vector of the nth particle, cross Newton's second law for the nth particle. When I do this and sum over, I can write the left hand side simply as g dt of summation of r I cross m I r I dot, and this follows from a step which we have seen before. That r I cross m I d dt of r I dot is d dt of r I cross m I r I dot. Now, why? Because if you take in this time derivative, you will get r I dot cross m I r I dot plus r I cross m I r I double dot. Now, this term vanishes because it is r I dot cross r I dot, that is 0. Therefore, what we are left with is the term that you will obtain by summing over the left hand side of all these individual equations. On the right hand side, I have summation of r I cross f I. Now, the summation of r I cross the sum of the internal forces, let us have a look at that. That will disappear because in that double summation I will have summation of r I cross, this is summed over I, this is summed over j f I j. So, this is what I will obtain from the second term on the right hand side. Now, this involves all forces with r I, r j, etc. Therefore, I will have terms like r I cross f I j plus r j cross f j I, and this being repeated for all particle pairs. Now, by Newton's third law, f I j must be equal to minus of f j I. Therefore, I can write this as r I minus r j cross f I j. Here I have written this term, as minus of f I j. F j I is minus of f I j. Then I take out f I j common, and what I have in brackets is r I minus r j. Now, r I minus r j is this relative vector, the vector joining particle j to I, and cross f I j. F I j is also, because this is an internal force acting between the ith and jth particle, it is also along that line connecting I j. Therefore, these two vectors r I minus r j and f I j are in the same direction. Therefore, their cross products must vanish. With that consideration, we are left with only summation of r I cross f I. On the left hand side within the brackets, what we have is known as the moment of linear momentum about O. You can check that m I r I dot, this term, this is nothing but the linear momentum of the ith particle, is the linear momentum of the ith particle indicated by G I, capital G I vector, and r I cross capital G I vector. So, moment of linear momentum about O, because all these position vectors are being measured from the origin of our coordinate system. Therefore, this bracketed expression is the moment of linear momentum of all particles about O, because there is a sum over. Moment of linear momentum of all particles about O. This is also known as the angular momentum of the system about O. So, the angular momentum of the system of particles about O. And on the right hand side we have moment of all forces about O. So, the left hand side says that the rate of change of angular momentum about O is equal to, from the right hand side, it is the moment of all forces about O. So, I have removed the clutter here. The time rate of change of angular momentum about O, which is indicated by capital H sub O, is equal to moment of all forces about O, which is indicated by capital M sub O. This equation, which we have derived from starting from Newton's second law, is now a new equation. It tells us about the change of orientation, as we will see very soon, is the rate of change of angular momentum. So, it has something to do with the orientation of the system. The generalized Newton's second law tells us how the system of particles, the center of mass of a system of particles is moving under action of forces, external forces on the system. This tells us how the orientation of this system is changing as the system moves, and we are going to interpret this very soon. This is written therefore as d dt of capital H naught equal to m naught, m o. So, rate of change of angular momentum about the origin is equal to the moment of all forces about the origin. If I integrate over time, straight away I will get the angular impulse momentum relation. The change of angular momentum as at two instants, if I look at two time instants t1 and t2, the change of angular momentum is equal to the impulse of the moment of all forces over this time interval. This is known as the angular impulse. The integral of moment over time is known as the angular impulse. So, this is the angular impulse momentum relation. If the net moment about O is 0, then the angular momentum will be conserved. Now, we are going to write down this expression of angular momentum, and let us see what it looks like using these vectors r I represented in terms of the position vector of center of mass and the relative vector rho I. And when I differentiate this, I get the velocity of the ith particle is equal to the velocity of center of mass plus the relative velocity of the ith particle with respect to the center of mass. I substitute back these expressions in the angular momentum relation about O, which is defined in this equation. Then I have these terms, these bracketed terms. Now, I will open up these brackets and simplify. And when I do this simplification, I always remember that summation of m I rho I is 0. The first term, for example, r g cross m I r g dot. So, we have it here. When I do this cross product with the second term in the second bracket, then I have this summation of m I rho I dot, which is 0. Therefore, that second term drops off. This cross this, once again I will get summation of m I rho I, that is 0. Therefore, that also drops off. Then this one cross product with this one remains like this. Therefore, I have only these two terms in the expression of angular momentum about the center of mass. I can therefore write it as rg cross m rg dot, which is the velocity of center of mass, plus this is because of the relative angular momentum. The first term on the right hand side is the angular momentum due to the motion of the center of mass. It is because of the motion of the center of mass about O that produces this moment of linear momentum of the center of mass, and the whole mass is concentrated at the center of mass. Therefore, it is the angular momentum due to the motion of center of mass with the whole mass concentrated at the center of mass. And the second term on the right hand side is the angular momentum due to the relative motion of the particles about the center of mass, because mi rho I dot is the relative linear momentum of the ith particle with respect to the center of mass, and rho I cross mi rho I dot gives you the moment of that relative linear momentum. Therefore, this is denoted by Hg rel, the angular momentum relative to the center of mass, angular momentum of the system relative to the center of mass. Therefore, the total angular momentum of this system of particles about O is the angular momentum because of the motion of the center of mass with the whole mass concentrated at the center of mass at G, the angular momentum because of that, plus the angular momentum because of the motion of individual particles about the center of mass. So, two terms contribute to the total angular momentum about G. So, this is our expression of angular momentum about G, and we have been using these expressions. If I replace only the second term here, r I dot, I write it like this. Then H G reduces to rho I cross mi rho I dot. Now, this is the angular momentum about the center of mass. The way we have defined in our previous discussions, we were defining the angular momentum about O, and that was taking the individual position vectors of the particles, taking cross product with the linear momentum of those particles. So, the position vector was measured from O. Now, what we are doing is we are trying to find out the moment of linear momentum about the center of mass. So, the angular momentum about the center of mass, and we will define it like this, that we take the linear momentum of the ith particle and rho I cross that linear momentum, and rho I is nothing but this relative vector from the center of mass to the ith particle. Therefore, the moment of linear momentum of the ith particle about the center of mass is rho I cross mi r I dot, and when you sum this over all particles, then you have the linear the moment of linear momentum of the system about the center of mass, or the angular momentum of the system about the center of mass. And we use these definitions once again and obtain this cross product. Once I open up this bracket and simplify, the first term you will note will go to 0 because summation of mi rho I is 0. Only the second term contributes, and that is equal to rho I cross m I rho I dot, and this is nothing but the HG_rel which we noted in the previous derivation for angular momentum about O. Therefore, the angular momentum about G, the center of mass, the angular momentum of the whole system about the center of mass is equal to the relative angular momentum about the center of mass. You should note a difference here in the definitions of Hg and Hg_rel, that here we have the absolute velocity of the particle, ith particle, here we have the relative velocity of the particle with respect to the center of mass. But finally, these two angular momenta, they turn out to be equal, Hg and Hg_rel. So, angular momentum of a system of particles about the center of mass is same as the relative angular momentum of the system about the center of mass. Now, for a rigid frame, this we have seen before, rho I dot, the relative velocity, rate of change of the relative velocity is nothing but omega cross rho I. When everything is connected by a rigid frame, therefore, the center of mass is in a fixed relation with the distribution of the particles, and in that case this rate of change of this relative vector rho I. So, rho I dot is omega cross rho I, which I can substitute in this expression of Hg or Hg_rel to express Hg in terms of the angular velocity of the frame. We continue with this angular momentum about the center of mass. If we take a time derivative of the angular momentum about the center of mass, then we have on the right hand side the time derivatives of these terms. The first term gives us rho I dot cross m I r I dot, and the second term gives us rho I cross m I r I double dot summed over. Now, I once again use those expressions of r I have used. So, here I have used this r I vector is r g plus rho I, and whose time derivative is this. So, that I have used here, and in the second summation m I r I double dot, that must be equal to. So, this can be written as the net force. So, force acting on the ith particle. And this, when simplified, gives us the rate of change of angular momentum about the center of mass is equal to the net moment of all forces about the center of mass. And this is an equation which defines the evolution, or this governs the evolution of the angular momentum of the system about the center of mass. So, once again let me reiterate, we have derived the generalized Newton's second law for a system of particles, which tells us the motion of the center of mass of the system. This equation tells us how the angular momentum is going to change about the center of mass for this system. Now, if I want to find out how a system of particles is behaving, then I must study two things. One is how this whole system is moving, or how the center of mass of this whole system is moving, and how this system is orienting as it moves. This governing equation tells us that rate of change of angular momentum, and this we will see very soon that this tells us how it is orienting, how the orientation is changing. Finally, we will find out the change of orientation of the system as the system evolves. So, to summarize, we have discussed the generalized Newton's second law for a system of particles. We have looked at the impulse momentum relation, and finally, we have defined the angular momentum and looked at the evolution of angular momentum about 2 points. We have looked at the evolution of angular momentum about a fixed point in inertial space, which was the origin of our coordinate system, and we have also looked at the evolution of the angular momentum calculated about the center of mass of the system. And as I mentioned, these two equations, the generalized Newton's second law for a system of particles and the angular momentum governing equations, they completely define the dynamics of a system of particles. The first one governs the motion of the center of mass. The second one is the angular dynamics or angular momentum, and this we will look at in a later lecture, how this tells us about the evolution of the orientation of a body or a system of particles. So, with that I will close this lecture.